Carnal embrace is the practice of throwing one's arms around a side of beef.
Is that all?
No, a shoulder of mutton, a haunch of venison well hugged, an embrace of grouse, caro, carnis, feminine, flesh.
Is it a sin?
Not necessarily, my lady, but when carnal embrace is sinful, it is a sin of the flesh, QED. We had caro in our Gaelic wars. The Britons live on milk and meat, lacte et carne vivant. I'm sorry that the seed fell on stony ground.
That was the sin of Onan, wasn't it, Septimus?
Yes. Yes, he was giving his brother's wife a Latin lesson, and she was hardly the wiser after it than before. I thought you were finding a proof for Fermat's last theorem.
Oh, it is very difficult, Septimus. You will have to show me how.
If I knew how, there would be no need to ask you. Fermat's last theorem has kept people busy for 150 years, and I had hoped that it would keep you busy long enough for me to read Mr. Chater's poem in praise of love, with only the distraction of its own absurdities.
Our Mr. Chater has written a poem?
He believes he has written a poem, yes. I can see that there might be more carnality in your algebra than in Mr. Chater's couch of eros.
Oh, it was not my algebra. I heard Jellyby telling Cook that Mrs. Chater was discovered in the gazebo in carnal embrace.
Really? With whom did Jellyby happen to say?
What do you mean, with whom, Septimus?
With what? Exactly so. The idea is absurd. Where did this story come from?
Mr. Noakes.
Mr. Noakes?
Papa's landscape gardener. He was taking bearings in the garden when he saw, through his spyglass, Mrs. Chater in the gazebo in carnal embrace.
And do you mean to tell me that Mr. Noakes told the butler?
No, Mr. Noakes told Mr. Chater. Jellyby was told by the groom who overheard Mr. Chater telling Mr. Noakes in the stable yard.
Mr. Chater being engaged in closing the stable door.
What do you mean, Septimus?
So thus far, the only people who know about this are Mr. Noakes, the landscape architect, the groom, the butler, the cook, and of course Mrs. Chater's husband, the poet.
And Arthur, who was cleaning the silver, and the boot boy. And now you.
Of course. What else did he say?
Mr. Noakes?
No, not Mr. Noakes. Jellyby. You heard Jellyby telling the cook.
Cook hushed him almost immediately. Jellyby did not see that I was being allowed to finish yesterday's upstairs rabbit pie before I came to my lesson. I think you have not been candid with me, Septimus. A gazebo is not, after all, a meat larder.
I never said my definition was complete.
Is carnal embrace kissing?
Yes.
And throwing one's arms around Mrs. Chater?
Yes. Now, Fermat's last theorem.
I thought as much. I hope you are ashamed.
I, my lady?
If you do not teach me the true meaning of things, who will?
Ah, yes, I am ashamed. Carnal embrace is sexual congress, which is the insertion of the male genital organ into the female genital organ for the purposes of procreation and pleasure. Fermat's last theorem, by contrast, asserts that when x, y, and z are whole numbers, each raised to the power of n, the sum of the first two can never equal the third when n is greater than 2. Nevertheless, that is the theorem.
Well, that has to be the all-time greatest lead-in ever written to the statement of a mathematical theorem. I think if there are any math teachers out there, you should take note. Something to be learned. I might add that Thomasina's next rejoinder to Septimus is, now when I am grown to practice it myself, I shall always think of you. To which I would add that from now on, whenever I see Fermat's last theorem, I will always think of carnal embrace. And Septimus in the gazebo with Mrs. Chater. At any rate, I should explain what it is that I'll be doing here today. I'll be playing the part of Eldon Pike, the American academician in Mr. Stoppard's new play, Indian Ink, whose role is to provide footnotes to the action as it goes along. So I'd like to start right in with my first footnote. Namely, about Fermat's last theorem, I don't know if you know the story of it, but it's worth retelling. It is one of the most unusual stories in all of mathematics. So first of all, Fermat lived in the first half of the 17th century, and he did many very important things. He had a number of contributions to mathematics, but oddly enough, he's most famous for something he did not do. Namely, he did not ever provide a proof of what is nevertheless called Fermat's last theorem. And in fact, the statement, which you just heard Septimus make so beautifully, was only found after he died. It was in the margin of a book he was reading, and it was found by his son, who went through his papers and wanted to publish interesting things. So there was no chance to question him on it a bit more. And the fact is, the statement he made, it was a little more detailed. He said, it is impossible to write a cube as the sum of two cubes, or a fourth power as the sum of two fourth powers, or any higher power as a sum of like powers. And so what does that mean? What does it mean you can't write a cube as the sum of two cubes? You take a whole pile of blocks, identical blocks, and you make a cube, say a 10 by 10 by 10 cube. He says you cannot separate them into two piles and make two exact cubes. There will always be some left over. And you can't do it for 10, you can't do it for any size. So that the number 10 cubed, or 1,000, is not equal to any other two numbers cubed added up. The same for fourth powers, and the same for higher powers. And then he added one of the most famous or infamous statements in the history of mathematics. He said, I have a wonderful proof that this margin is too narrow to contain. So there it was, and people tried to reconstruct his proof or find their own. It took about 100 years before even that first case was done, the cube. That was a famous Swiss mathematician, Leonhard Euler, in the middle of the next century, who was able to prove you could not write a cube as the sum of two cubes. Fourth powers was the thing that Fermat did. He did show that you cannot write a fourth power as the sum of two fourth powers. My guess is that he was mistaken. He thought from that he could go the whole way, that the same method would work. Turns out that that's a very special case. The method he used, it's very ingenious, but it works only for fourth powers. And that's where it stood at the time of the play. This opening scene took place in 1809. As Septimus said, the theorem had been around for 150 years, and only the first two cases for third and fourth powers had been shown. Well, in the 200 or so years between that time and 1993, when Arcadia first opened in London, lots and lots of mathematicians had tried to prove the theorem, always unsuccessfully, but they'd made a lot of progress. By the beginning of 1993, it was shown a mathematician named Joe Buehler, who's at Reed College, and his colleagues, using computers, showed that Fermat was right for all powers up to 4 million. Now, that's fairly convincing evidence, but you've got just as far to go from 4 million to infinity as you had when you started. So that as far as a proof of the general theorem, you were really nowhere near it. Then, as I say, Arcadia opened with this wonderful beginning scene about Fermat's last theorem, among other things. And in April, and 2 months later, a mathematician at Princeton, Andrew Wiles, went to a meeting in Cambridge, England, and announced he finally had a proof of the complete theorem. He had been working in secret for 7 years after Ken Ribet, a mathematician at Berkeley, had shown that there was a connection between Fermat's last theorem and other parts of number theory. And at that point, Wiles decided this was what he wanted to do with his life. Only in the last few months did he confide to some close acquaintances that he was working on it. Once it was announced, then front page newspaper reports all over the world, and then a BBC television documentary that Nova took over called The Proof, which some of you may have seen. lots of publicity. My first question is, did you have any whiff that Wiles was onto this, that this was about to happen? No inside information?
None whatsoever. But it was curiously gratifying. We slipped the program in the theatre with copies of the story in the Times announcing Wiles's proof. I'm not sure offhand whether we withdrew the slips when Wiles partly withdrew his proof. And by the time Wiles came back with the reinforced proof, everybody had forgotten about Wiles in the theatre, until this moment, of course. I must say that the television documentary to which you referred, I think, if it's the same one, was a BBC film.
Yes. Yes.
Under the aegis we call Horizon. And I watched it a couple of times. I do recommend it if anybody's interested in this sort of thing. It will possibly do for the people who are here because of their interest in drama, as opposed to the people who are here for their interest in mathematics. It will probably do for you what it did for me. It'll make you understand Fermat's last theorem for about 12 minutes. Unless you attempt to explain it to a third party, in which case you find you don't understand at all. As a postscript to that, perhaps I might also mention that when Thomasina, the young woman, leaves the room at the end of the scene, she's got rid of by she's saying, well, extra spoonful of jam with your rice pudding if you find the proof of Fermat's last theorem. And she goes out with the announcement, there is no proof.
Wait.
Oh, are we going to have it?
That's coming.
You're not doing the whole play, surely?
No, but we wanted that line.
I see. Oh, well, I'm sorry. The suspense will be bearable, I'm sure.
Yeah. Well, let me ask you, how did you know about Fermat's last theorem? It was not at that point common knowledge.
I really cannot tell you when I first heard the phrase and when I first understood what it meant, but I have no particular background in mathematics, and I'm probably like a lot of people here. I have quite an appetite for and a general ability to take in information which reaches us at the level of the airport paperback, which is fine. I mean, I have no erudition in this discipline. I wrote another play which, I don't know what the verb is, utilized quantum mechanics as a kind of metaphor for dramatic purposes. I have no erudition in physics or in mathematics. I have a fascination for the discipline. I like talking to people who know about it. I like reading about it to the level of my understanding and a bit beyond. I have no expertise, and I don't think I've got any talent in that direction. But I do find mathematics deeply potent on some level, which I think it would be doing it less than justice to call it a metaphysical level. But in the case of this play, I'm not, this is a parenthesis now, I don't use my life when I write plays. I use thoughts which I encounter or which encounter me. And I stumbled into a very good journalistic book about chaos. And I'm always desperately on the lookout for something to write a play about, because I don't have any bottom drawer, you know, where all this stuff is waiting to be fleshed out. And rather as quantum mechanics struck me as being an extremely potent metaphor for something. Your reproach is well merited, because I felt it was a very good opportunity, and it took me a while to figure out that for me it was a good metaphor for the John le Carré world of spies and double agents and so forth. In the case of Chaos and Arcadia, and Chaos is only an aspect of the background to this play, there's almost a dislocation which I yoke together with violence between stuff which I just enjoy reading about on the one hand, and on the other hand, the quite separate desire to write plays, be part of the theater, and justify my existence with a play if I can. And so I was really on a quest for a validation of chaos mathematics for a play. I was just looking for any kind of play which I could use it, because I liked to find out about it and it interested me. I was looking for any kind of play which wouldn't make the mathematics in the play look gratuitous. And the result is this particular play. And I hope that it's not gratuitous. It's quite tricky to differentiate. I mean, for the writer to establish a differentiation between the mere repetition, exposition of stuff which I'd read, on the one hand, and the use of it in a fertile form, in a form which has its own organic ability to generate thoughts in the audience and resonate among the characters in the play and resonate amid the actions of the play. I have no clue as to how succinct we're supposed to be. You know, I can go on like this for hours.
Unfortunately, I can too, but people are here to hear you. But let me ask you, a friend of mine, a mathematician at UCLA named Barrett O'Neill, told me that about 7 or 8 years ago, he was flipping through the radio dial and came across a play where 2 telephone answering machines were giving messages, one of which said, "Can we talk about Augusta?" And it went on, it turned out to be Byron and so on. And it sounded from his description like it was an early version of Arcadia without the mathematics. Was there such a thing?
I've never heard of it.
That's very interesting.
Maybe another answering machine wrote it.
It could be. I'll get more information from him. That's very interesting. I wanted to ask you about the character of Thomasina, as a matter of fact. I mean, here she is, this 13-year-old, very precocious sort of mathematical prodigy, which by itself is not a usual character for a piece of theater, but also I think most people think of kids who are prodigies in math as being boys rather than girls. And I wondered if, did you have why you made this choice? Was there any particular model you had in mind for Thomasina, or
no,
how did you?
And not Byron's daughter either.
It wasn't, because everybody assumed it was Byron's daughter.
There's no special social significance in making her female. It's more to do with getting a balance. I mean, there's a tutor and a pupil.
Right.
And I don't even remember the thought processes. I rather felt that a tutor teaching a young woman was more unusual at that period. I think that was part of it, come to think of it. In 1809, tutoring a girl in respectable mathematics and other disciplines would be less usual than doing so with a boy,
right,
a young boy pupil. But I don't recall how it all worked out or where it came from. I really don't.
Yeah, I should say, if people don't know about Ada, that she actually is a fascinating story, that Byron's daughter, his only legitimate daughter, who was very interested in mathematics and later became famous, went on and working with Babbage on his prototype of computer. You probably all have a subliminal picture of Ada in your mind, because every Microsoft product, if you look at the certificate of authenticity, the watermark is a portrait of Ada. Oh. So any of you want to see what she looks like. But that was one case. There's another one that I thought you might have come up with, is Sophie Germain. Do you know about her?
I do, but I didn't know about her then.
I see. Because she was another mathematics prodigy, and in fact, several parallels with things that happen in the play. When she was young, she had not only no tutor, she discovered math books on her father's shelf and got fascinated by them as a teenager, but her parents were aghast. This was not proper upbringing for a young girl. And the story goes that she had all candles taken away from her at night and no heat in the room, so she would have to go to bed and sleep, and she smuggled candles into her room and stayed up late and studied the mathematics. And at this period, she was working on number theory, and in fact, one of her most famous things later was a contribution to Fermat's last theorem.
When was this?
When she started doing number theory, she was born in 1776.
Oh, right.
And so she was doing number theory in exactly 1800 to 1809, just that period. But the Fermat's last theorem came later, around 1820, and in fact it led to the next case being settled of the fifth powers in 1825, using what she did, and then Dirichlet, a French mathematician named Legendre, who was over 70 at the time, proved the next case, which is a heartwarming story for some of us. But at any rate, she was definitely a possible prototype. But it's interesting, there are these parallels, but they were not what you had in mind, in particularly.
Rightly or wrongly, I mean accurately or inaccurately, I made her, in every other respect, a perfectly ordinary young woman. I mean, I find the character attractive for that reason. Yes. And I feel this. Oh dear, is this true? Do I believe this? The idea of genius in novels and in art, the idea of genius in art very often presents us with most unusual kind of human beings, and one of the unusual things about them is that they're very, very clever, but it's not the only thing. And I guess that when one thinks of Gödel, for example, in life that may very well be also true, that you'd notice these people if you saw them on a train, they wouldn't, and so forth. But I like to think that they are perhaps the egregious ones, and most very, very clever people. I find this an attractive idea, that if there's 10 people messing around with a basketball in a court there, one of them could be the genius, but you wouldn't know which by just looking at them and listening to them. And I like that aspect of that character.
I had an interesting experience years ago. I visited Dartmouth, and somebody was trying to introduce me to a mathematician who became a very leading one later, who I hadn't met. And they said, here, he's working on a house, and there were all these people on the roof building a house, and they said, no, I won't tell you which one he is. You pick him out. And it was absolutely impossible. I could not recognize the mathematician.
I remember there was when Bertrand Russell spent some time in prison for, I suppose, political actions, disgracefully so. He spent some time in prison. There was an excellent cartoon of a prison breakout with a couple of very thuggish people, and Bertrand Russell standing by a hole in the fence. They'd just been captured. And the guards were saying, okay, which of you is the brains behind this?
I have one more question about Thomasina. The name is striking under the circumstances. Is there anything of you in Thomasina?
No, I mean, I had to get past that particular, false assumption. I mean, I like the name. I don't know why. It wasn't. I mean, as a female,
right.
I don't like my own name much. I never did like Thomas as a name, but Thomasina I liked as a name. Just to indulge my incipient capacity for pretension for a moment. It's as though fictitious characters already have names, and one has to try and figure out what their names are, and hers was Thomasina. That's how I get there.
So, when you were a young teenager, you didn't have a fascination for any of these subjects that she does, or?
No, but the nearest I had to ability was frustration. If you don't like it or want to do it, you're not going to be frustrated. And something in me liked it and wanted to do it. So,
well, that's worth a lot. In fact, I think that may be reflected in your writing. But why don't we hear some more from Thomasina and Septimus, and then we'll continue.
Septimus, do you think God is a Newtonian?
An Etonian? Almost certainly, I'm afraid. We shall have to ask your brother to make it his first enquiry.
No, Septimus, a Newtonian, Septimus. Am I the first person to have thought of this?
No.
I've not said yet.
If everything from the furthest planet to the smallest atom of our brain acts according to Newton's law of motion, what becomes of free will?
No.
God's will?
No.
Sin?
No.
Very well.
If you could stop every atom in its position and direction, and if your mind could comprehend all the actions thus suspended, then, if you were really, really good at algebra, you could write down the formula for all the future, and although nobody is so clever as to do it, the formula must exist just as if one could.
Yes. Yes, as far as I know, you are the first person to have thought of this. In the margin of his copy of Arithmetica, Fermat wrote that he had discovered a wonderful proof for his theorem, but the margin being too narrow for his purpose did not have room to write it down. The note was found after his death, and from that day to this...
Oh, I see now. The answer is perfectly obvious.
This time you may have overreached yourself.
The thing that is perfectly obvious is that there is no proof, Septimus. The note was a joke to make you all mad. Alpha minus? Pooh! What is the minus for?
For doing more than was asked.
You did not like my discovery.
A fancy is not a discovery.
A jibe is not a rebuttal. I think it is an excellent discovery. Every week, I plot your equations dot for dot, x's against y's, in all manner of algebraical relation, and every week they plot themselves as commonplace geometry. As if the world of forms were nothing but arcs and angles. God's truth, Septimus. If there can be an equation for a curve like a bell, there must be an equation for one like a bluebell. And if a bluebell, why not a rose? Do we believe nature is written in numbers?
We do.
I will plot this leaf and reduce its equations. You will be famous for being my tutor when Lord Byron is dead and forgotten.
That last line was one of the reasons I thought of Ada. I don't know if you were aware that Byron's daughter I believe in a letter to Babbage, said at one place, what was it? She said that, "I do not believe that my father ever was or could be such a poet as I shall be an analyst," which seemed to reflect this sort of a boast. But no, it was not Ada you had in mind. There are a couple of other statements there I just wanted to ask you if they reflected anything in particular. One of them was this: do we believe nature is written in numbers? What were you thinking of? Was there something particular there, or?
Well, how far back does that one go?
Long way.
A long, long way.
Yeah.
Well, certainly as far as Pythagoras, taking nature in every sense. I think that the idea that the natural world, now let me get this right. I'm not that fascinated by the idea that the natural world can be written in numbers. I'm not that fascinated by the proposition that the numbers are, as it were, determining the shape and form and activity of the natural world. What is really, really interesting is that those two statements are equivalent to each other and are not, in fact, rival attempts to describe anything. That there's a complementarity about the notion that math describes nature and that nature is following mathematical rules. I suppose the thing about chaos mathematics is there's an aspect of that which is expressed in a single line later on. You'll tell me that the line is going to be performed, but it doesn't matter. It's not an ambush. It's fine. And the idea that the equations of chaos, when applied to the natural world, for example, as we'll probably find to goldfish, population biology, whatever. But the notion that these equations, or that the theory does not describe the behavior of fish, but describes the behavior of numbers, that is really a spooky idea. I still find it spooky after all these years.
You mean that numbers imitate fish, or what?
No, no. Oh, well, that might be something too. But the fact that the equations can describe behavior in utterly disparate fields, perhaps in zoology here, economics there, suggests that, I'm not sure if I've got the right vocabulary for this, but there's a suggestion that numbers have a kind of social behavior, that they're not simply tools of description. Or at any rate, that this is getting deep, isn't it? That equations have as it were, a behavior. I think that the notion of nature being written in numbers is possibly the most acceptable and perhaps reassuring idea in the whole relationship between life and math.
I'm not sure everybody accepts it, but it's true that it's a guiding principle for many people, and certainly many scientists like Kepler who felt that this was the way to find out how nature really worked.
Well, but I mean, the fact of the matter is, what a dangerous statement. But am I wrong about this? That that we're now on the edge of finding mathematical descriptions of events in nature which have always seemed not merely unsolved, but beyond solution, such as turbulence, for example. Isn't that the case?
I would say no, but at any rate, it's always been true that we found whole new areas to which it hadn't been applied before, where we couldn't see how mathematics would be applied. In fact, we'll see later, just this period, around early 1800s, was a huge ferment and a deliberate policy in France of looking for new areas that had never been approached and that could be described mathematically. And also, that was the time, I guess there was another statement I wanted to bring in here. This one when Thomasina says, "Am I the first to have thought of this?" And then she makes this statement that if you knew the positions and velocities of every particle, you would know the whole future. Did you have a particular model in mind for that?
Well, I knew she got there just in front of Laplace.
Okay, I was wondering if you did, yes.
Yeah.
Yes, she came to it just before Laplace had made the standard formulation of this. I actually...
there was also...
Yeah.
Oh, no, carry on.
No, I was just going to say, it's one place I didn't do my footnote homework and find the exact date, but I know it's close. What were you about to say?
1820-ish, I think.
It was around there, yes.
You were going to say?
No, you were about to say something.
No, I mean, look, I've come all this way to Berkeley. I better get an education while I'm here. No, I'm actually interested in this. This is not... You must interrupt me because I'm not leading to anything, but is it... I mean, who has the majority here in the world of mathematics and, well, in the world of science? Who has the majority here? Are we saying that there are all kinds of phenomena and events which are not reducible to maths?
No, that's not what I was saying. I was saying that there are many that we're not close to, and that may or may not.
Oh, I didn't. Yes. Okay, I didn't. Sorry. Okay, I said on the brink of.
On the brink of.
I withdraw that.
That was the thing I was objecting
that
to.
was the less interesting. For me, that was the secondary issue. What I really meant was that the principle is sound, that the phenomena and the behavior appear to be reducible to mathematics, which may elude us for a very, very long time, but nevertheless is there to be discovered. Would you say that's a reasonable proposition?
Yes, but a debatable one, obviously. Some people believe that very deeply, and other people do not.
I mean, is randomness, I mean, true randomness, a force in nature?
Well, clearly, first of all, true randomness turns out to be one of the hardest things to define, even what it means. But clearly, let me get back. In fact, let me circle around and come back to this.
Am I raising the level here too far?
You are. It's wonderful.
Am I losing you?
I was warned not to do this.
No,
so you're.
I'm sorry. I really go. No. Stop joking now.
See, Laplace was probably most famous for writing his book on the system of the world, several volumes, where what he did was to carry this Newtonian determinism, which gets referred to. Maybe I should back up and say a few words about Newton and then what it was that Laplace did. Newton was one of these very rare people who was both a top mathematician and top physicist. And in mathematics, he did many things, one of which was invent, if you like, or develop the calculus, although there was this whole controversy later whether Newton or Leibniz had priority, but that's fairly irrelevant. And then as a physicist, he did all his experiments on optics and all. But most importantly was this area in between where he wrote his laws of motion and the law of universal gravity. And then it seemed from that you could deduce everything. In particular, he deduced Kepler's laws, that planets go in ellipses and so on. So this is where the notion first originated, although not really with Newton, because they were a long way from understanding everything. In fact, it's not true that planets go in ellipses. If the universe consisted of one sun and one planet, the planet would go in an ellipse, but all planets pull on each other. And that was far beyond the capabilities of Newton and all, until Laplace was the first one who really had the mathematical power to put this all together and describe the whole solar system in a fairly satisfactory way, and far beyond. He was the first to suggest that there could be something that was what we would now call a black hole. Laplace specifically mentioned that if you had a heavy enough object with enough gravity, that light would not escape. So that what he did was carry this Newtonian philosophy to the degree where it seemed like this was real. You could answer all questions, basically. In fact, there's a famous story about dialogue with Napoleon. Laplace was one of Napoleon's inner circle. Napoleon loved to discuss science and mathematics and philosophy with him. And of course, he gave Napoleon a copy of his book on the system of the world. Napoleon apparently asked him, how is it you've written this huge book and you never mention the author of the universe? To which Laplace is supposed to have answered, sir, I have no need of that hypothesis. So this is sort of the duel of God being a Newtonian. At any rate, it's not in that book that he makes this statement about knowing the whole future. That's in a later book on probability. And it's in the context of saying almost the exact opposite. Yes, if you really knew the position and velocity, and if you really had the mathematics, you could do this. But we don't. We don't know either of those. And in actual fact, almost everything we can do has to be on a partly probabilistic basis.
Well, he was very early on probability.
Yes.
Interestingly or otherwise, my imagination broke down at a certain point. I mean, the penny or the other shoe didn't drop until much, much later. But what Thomasina says about this hypothetical equation telling you of the future, I hadn't quite got that it also does that for the past.
No, yes.
And you can, as it were, authenticate history by the same equation. But when I don't want to get too stuck in the same little subject, but when she points out that, or when she hazards that, if there's an equation which produces a bell curve, surely there has to be one which could produce a bluebell, and if a bluebell, why not a rose, which just seems much more complicated. And I'd like to ask you, I mean, in a certain sense, in a sense which you couldn't possibly understand then, is it in fact the case that the flower arrives at its ultimate form through molecular, particular actions which follow the laws of quantum mechanics generally? I mean, is that
in a certain sense, it has to be.
Is that a meaningful idea?
It's made up of molecules, and they follow specific laws.
That's my thinking. How can one get around that?
Well, the question is, how do you, in any sense, get from the molecular level to the genetic level and the genetic level? Do it in any concrete sense. Are there gaps there? I mean, certainly we can't do it in practice. And in fact, there's a whole question which I want to get to later after the next scene that has to do with heat, which is a major issue in the play and also was being studied at that time. But the bell curve, did you realize that this was in fact one of the things Laplace was working on at this time? So the equation of the bell curve was current big news at the point that Thomasina refers to it. And Gauss had also just written on the bell curve at that point.
It's not so much what the equations are, But
it's that there should be.
Well, I mean,
there are two separate questions. One is there an equation?
yeah.
And I thought you might have been referring to Fourier at that point. When I went to college and was studying mathematics, I remember at one point the teacher saying, the wonderful thing is you can draw any curve you want on the board, and using what's called Fourier series, you can write down an explicit equation. So that in some sense, yes, there's an equation. But then this is a different genitive sense, that you can derive the shape from mathematical laws.
Well, the generation of shape, and this is really what's so great about her, if we pretend, she's a real person now for the moment.
Right.
What's so great about her is that what she understands in a sort of way, or ultimately seems to stumble into, that it's not actually the equation in itself, it's the way you actually manipulate the equation, the way you pull the solution back into the equation in a feedback loop, which generates shapes. And I think that, in the end, is what is moving about the idea that nature is written in numbers. That is generative, not simply a kind of applique. Here's a phenomenon, here's an equation. Wow, they fit. That's not really so moving. It's the idea that there's something yeast-like in the numbers, which is somehow behaving.
Right. Well, I think this actually leads in very naturally to the next scene, so why don't we go on to that now?
I, Thomasina Coverley, have found a truly wonderful method whereby all the forms of nature must give up their numerical secrets and draw themselves through number alone. This margin being too mean for my purpose, the reader must look elsewhere for the new geometry of irregular forms, discovered by Thomasina Coverley. Does it mean anything?
I don't know. I don't know what it means, except mathematically.
I meant mathematically.
It's an iterated algorithm.
What's that?
Well, it's... oh, Jesus. It's an algorithm that's been iterated. How am I supposed to... The left-hand pages are graphs of what the numbers are doing on the right-hand pages, but all on different scales. Each graph is a small section of the previous one blown up. Oh, like you blow up a detail of a photograph, and then a detail of the detail, and so on, forever. Or in her case, until she ran out of pages.
Is it difficult?
The maths isn't difficult. It's what you did at school. You have some x and y equation. Any value for x gives you a value for y. So you place a dot where it's right for both x and y. Then you take the next value for x, which gives you another value for y. After you've done that a few times, you join up the dots, and that's your graph of whatever the equation is.
And is that what she's doing?
No. Well, not exactly. Not at all. What she's doing is, every time she works out a value for y, she's using that as her next value for x, and so on, like a feedback. She's feeding the solution back into the equation and solving it again. Iteration, you see.
And that's surprising, is it?
Well, it is a bit. It's the technique I've been using on my numbers, and it hasn't been around for much longer than, well, call it 20 years. See, when your Thomasina was doing maths, it had been the same maths for a couple of thousand years. Classic. And for a century after Thomasina. Then maths left the real world behind. Just like modern art, really. Nature was classical, maths was suddenly Picasso's. But now, nature's having the last laugh. Freaky stuff's turning out to be the mathematics of the natural world.
What are you doing?
Actually, I'm doing it from the other end. She started with an equation, turned it into a graph. I have a graph, real data, and I'm trying to find the equation which would give you the graph if you did to it what she did to hers. Iterated it.
What for?
It's how you look at population changes in biology. Now, goldfish in a pond, say. This year there are X goldfish. Next year there'll be Y goldfish. Some get born, some get eaten by herons, whatever. Nature manipulates the X and turns it into the Y. Then Y goldfish is your starting population for the following year. Just like Thomasina, your value for Y becomes your next value for X. The question is, what's being done to X? What is the manipulation? Whatever it is, it can be written down as mathematics. It's called an algorithm.
Can't be the same every year.
It's not about the manipulation of fish. It's about the manipulation of numbers. This thing works for any phenomenon which eats its own numbers. Measles epidemics, rainfall averages, cotton prices. It's a natural phenomenon in itself. Spooky.
A mathematics whereby all the forms of nature must give up their numerical secrets and draw themselves through number alone. This feedback, is it a way of making pictures of forms in nature? Just tell me if it is or it isn't.
To me, it is a picture of turbulence, growth, change, creation. It's not a way of drawing an elephant, for God's sake.
I'm sorry. So, you couldn't make a picture of this leaf by iterating a what's it?
Oh, yes, you could do that.
Well, tell me. Honestly, I could kill you.
If you knew the algorithm and fed it back, say, 10,000 times, each time there'd be a dot somewhere on the screen. You'd never know where to expect the next dot, but gradually you'd start to see this shape because every dot will be inside the shape of this leaf. It wouldn't be a leaf, it would be a mathematical object, but yes. The unpredictable and the predetermined unfold together to make everything the way it is. It's how nature creates itself on all scales. The snowflake, the snowstorm. It makes me so happy to be at the beginning again, knowing almost nothing. People were talking about the end of physics. Relativity and quantum looked as if they were going to clean out the whole problem between them, a theory of everything. But they only explained the very big and the very small. The universe, the elementary particles, the ordinary size stuff, which is our lives, the things people write poetry about, clouds, daffodils, waterfalls, what happens in a cup of coffee when the cream goes in. These things are full of mystery, as mysterious to us as the heavens were to the Greeks. We're better at predicting events at the edge of the galaxy or inside the nucleus of an atom than whether it'll rain on Auntie's garden party 3 Sundays from now. Because the problem turns out to be different. We can't even predict the next drip from a dripping tap when it gets irregular. Each drip sets up the conditions for the next. The smallest variation blows prediction apart, and the weather is unpredictable the same way. Will always be unpredictable. When you push the numbers through the computer, you can see it on the screen. The future is disorder. A door like this is cracked open 5, 6 times since we got up on our hind legs. It's the greatest time to be alive when almost everything you thought you knew is wrong.
Does that over-dramatize the situation?
Perhaps. But, there's so much to talk about in that dialogue. I think we could easily spend an hour on that. I wanted to ask you a few general questions first before getting to the specific content. The character of Valentine, as a mathematician or a mathematical biologist, I guess you talked before about having characters who have these sort of special interests. I just wonder how you picture him as a character. I should preface to say that I saw the play put on at ACT here, and then I saw this performance in Paris, which I believe you went to last fall also. And there was striking difference in the way Valentine was portrayed. In Paris, it was very much a stereotype of the totally misfit mathematician, socially awkward, and so on. How did you picture Valentine? Was it?
Yes. Also, it was in French too. I confess.
Paris is the capital of France. Yes.
I was so forcibly struck by that distinction that I haven't really noticed any others. The character, he's a postdoc. I guess he's some kind of he's at the mathematics end of zoology, isn't he? He's doing populations, and I mean, we touched on this. I find that you shouldn't be able to tell from his other conversation and from his general appearance that he's, well, first of all, he's not a genius, so we're talking about different things here. But, well, actually, you know, one of my kids, my eldest kid, he did a science degree at Bristol. I think I was thinking about him some of the time. I hope he comes over as a character in a story, who serves the purposes of the story, not the purposes of some sense of what scientists must be like.
More generally, I wanted to ask, you know, Arcadia has been such a success. It's being performed all over. People love it. Those who missed the performance in San Francisco, there'll be another Northern California production in a few months. The Actors Theater in Santa Rosa going to mount Arcadia. The conventional wisdom is if you put that much heavy mathematical dialogue, you'll frighten away audiences in droves.
Well, hang on a minute. I mean, let's just clarify something.
Yes.
It's all fine by me, but there must be many people here who don't know the play. And one should say for them, that actually what you're watching are the scientific bits which suit this occasion being pushed together. Believe me, you're very sweet about the play. It would not have been done in very many places if 2.5 hours of it were like this. So we've left out, I say we, I just come and see what we got here, and it's fine. But the middle of scenes is left out and so forth. But that said, yes, continue. Yes, that's fine. I just want to make that point. That it's not. It's for the drama element here. That isn't how to do it.
No, but nevertheless, you don't shy away from including it. I mean, this is what I find remarkable.
Well, I mean, the difficult part, but also it's intensely interesting to me, so it's not difficult in a disagreeable way, is to try to be plain without being prolix. I mean, there's a play called Copenhagen by Michael Frayn, which is a play about Heisenberg, and whatever it's about, it has to deal with quantum mechanics. Well, is that fair? It deals with what was happening in physics in the 20s and 30s.
Right.
I think it's a miracle, that play, because it actually is, for me, it's clear and it's not at all prolix. I think it's a wonderful achievement. And it's a three-hander, and one day maybe you'd have Michael sitting here and you can have a symposium. It'd
Wonderful
be really
idea.
good. You should. I'll recommend it. To him, I mean. So, I mean, what do we just have? I mean, in a way, we anticipated that scene without meaning to, because I didn't know what was coming up. I think that the notion of the young man being pleased because he senses that there's still a lot to do, I find that endearing, and I hope true of young scientists.
I think it is. Yeah.
Because it must be dispiriting to have somebody like the guy who wrote The End of History. You know, if you're a
And
historian,
the end of science. There is also the
end of science too.
Yes.
Well, I see the editor of Nature has just published a book called What Is Left to Be Discovered. Has he not?
I haven't seen that one.
Well,
Much.
I think that speech of his rings something of a chord with me. It strikes some kind of chord. Because, of course, the great advantage of art is that the question of is there any left, that doesn't arise. It's like philosophy. It's not supposed to make progress.
But I don't totally agree, because
I know, nor do I. It's okay.
Yes. There are periods when some art form seems used up, and then a whole new direction has to come along to
Well, a
revive.
particular, yes, you know, you might say that, I don't know, Syrian music or something comes to a point, but
Right.
but the notion of art is, I think, by definition inexhaustible, because our humanness somehow is involved. There are no, I mean, I'm not a, you know, I'm not an absolutist, and I'm not a relativist. It's a tricky area, this, for me. But self-evidently, art very often, whether it's a style of painting, or whether it's a style of composition in music, whether it's plays in the theater, very, very often it appears to have, well, let's put it crudely, a sell-by date. It really does. I'm under no illusions about Arcadia by Tom Stoppard. You know, there's a very nice piece in Evelyn Waugh's autobiography where at the back of the books in the old days, publishers used to put advertisements in for other books in their list of that season. And I think it was one of his first novels was published with such an advertisement in the back for books praised beyond, oh, it clearly wasn't his first novel, but praised beyond anything that Waugh had received in the way of praise, or totally forgotten.
Right.
It's hard to tell what's going on here.
But there's the other way
the
around, too.
Which is?
Books ignored at the time, and then later
Clearly, absolutely.
become classics.
But there's never, in the arts, the equivalent of a theory of everything. There's nothing encompassing like that.
Well, some of us have doubts that there's a theory of everything in science, too.
I see that, but that's a different point.
Yes.
You find the conception intelligible. That's the point.
I really don't. I personally don't.
You don't?
No.
You think that's a meaningless phrase?
Yes,
Really?
almost in the sense that Laplace said that there is so much that we don't know, which by far exceeds the little bit that we've been able to figure out. Mm-hmm. And, you know, people give all the examples of understanding the mind and how the brain works, and we are so far, despite a lot of real progress, from really understanding, and so much, well, as he says, we can talk about the whole universe and subatomic particles better than we can talk about whether it will rain next Sunday. and a picnic. And there are many, many things which we may eventually, well, turbulence, you know, we may get little insights. But to fully understand, I don't see an end to it, not as long as it's human beings who are doing it.
There's something here which is a real distinction, though it appears to involve one in metaphysics if one talks about it for more than a minute. But this character is talking about certain scientific ideas, propositions. You know, are they good or bad, we say? You know, are they true or false? But let's say good or bad. It seems to be the case that in the case of these particular propositions, consensus is very, very important. You know, if enough of you say, yeah, this is good, that in a sense is its authenticity. In a certain sense, that's its authenticity. All you guys agreeing, yeah, that is true. I believe that. I think you've cracked it. That's true. Well done. And thousands of us say you're right, and that's good. Now then, you know, you're being generous about the play which contains this scene. You're saying all these productions of Arcadia all over the place, and people like the play a lot. But to say that, therefore, it's good is not the same statement.
I didn't say that. I think it's...
I'm not saying you said it, but I'm saying that, that there is, you know, in the end, discussions get interesting when there's a failure of vocabulary, when the vocabulary simply doesn't offer what we're really talking about. So good art and good science are sort of a failure. Those phrases are, in a sense, a failure of vocabulary. And the reasons why it's a failure is what artists should be addressing, while the scientists get on with the improved image, you know, universe. Fine.
I wanted to ask you a related but somewhat different general question, and that is, given the enormous, again, current critical and popular success of Shakespeare in Love, does that motivate you more to want to turn Arcadia perhaps into a film? And if you did, could you leave in all these parts, or would you have to abandon them in that medium?
I don't know, but I think that, you know, it's only purposeful in a limited way to photograph a play. So we're not talking about that.
No.
To make a movie of Arcadia would entail leaving out quite a lot of the play. So we're talking about something else. I actually did think about it 2 years ago, nearly, and I didn't pursue it very far, partly, I hope this isn't an awful thing to say, partly because I wasn't that interested. You know, getting back into Arcadia, and having to get back to where I was when I was writing it, and to get equally somehow juiced up to deal with it all and go off this way and that way, I couldn't do it. So it became a rather technical business, how to make it's also a strange alchemy, turn a play into a movie. People jump up all the time and say they want to do a movie of this play or that play. It never seems to get anywhere, and I think I sort of vaguely understand why. Shakespeare in Love is a different sort of thing anyway.
Sure.
You know, I'm not sure. I literally don't. I mean, unless you're saying, "Oh, find an audience." You know, here's the audience. This actual one. They'd live with a movie of Arcadia. You just use everything. and make it look beautiful and move the camera a bit, and there's your movie. But actually, it wouldn't be as good as the play, because one of the, the great advantages that playwrights have, directors, actors, is that the here and nowness of theatre is something which is, there is no substitute for. And I don't mean that in a kind of thing, oh my God, we're actually here and now, do the show right here. What I really mean is that you're watching the thing, and you're watching it in a certain frame of mind, which includes the knowledge of the physical limitations of the space we're all actually inhabiting for these 2-3 hours. That operates on the way you receive what you're looking at. So you can do extraordinary magic, which depends upon those limitations. A friend of mine told me once about this. I'll make this very quick. Well, actually, there could even be some science in it. Who knows? So, astronomy. It was a production of The Tempest in the open air. It was at an Oxford college. This is grass, here's a lake, you're all sitting in the garden, you're watching The Tempest in a real light. The evening starts to close in around the play, and at the moment, the time comes where Ariel makes his exit from the action. And so he runs along the grass, reaches the edge of the lake, and just runs across the top of the water, plish, splash, because they'd put a boardwalk just an inch underneath the water. And then the darkness kind of swallowed him up, and you could hear his feet just splashing into the distance. And then as he reached the further shore, and it was completely obliterated by the gloom, a firework rocket was ignited, and it went whoosh into the air, and it burst into all these sparks, and all the sparks went out, and he'd gone. And then when you actually look it up, it says exit Ariel. So movies can give you that weird lift, but they do it on completely different level in other ways. They can't do what happens when Thomasina and Septimus dance and the candle is there. I don't know what they can't do it.
Yes.
So that's what is that. It's the science of something.
Yeah. Well, yes. I guess what I would like to do at this point is anticipate a bit the next scene. One thing that's so marvelous, we talked a little beforehand, you managed to find all these different threads. As you said, Arcadia has many different themes and threads that go through it. And you find the timings so magnificently that come together just at this period. There is this issue of the waltz, which surprised me because I would have thought, the last scene is in 1812, by the way, and I would have thought that waltzing became big much later on, but I consulted my loyal OED, and it turned out no. In fact, just around this period, it was spreading throughout Europe and it became the big thing. And in 1812, Byron wrote The Waltz, which, did you know about that? I didn't either. There it is. There's also this definition of the waltz in a music and art dictionary. And what did it say? I'm going to get this wrong. Yes, I can't think of the exact word. It wasn't an obscene dance, but it was something like that from Germany. So an outrageous dance.
Well, it was the first time where you were allowed to hold your partner.
Right. And, well, yes.
It's a scandalous dance as opposed to doing all the Jane Austen kind.
That was the next stage. But the other part of timing, so again, this last scene is perhaps May of 1812 by my computation. In January of 1812, in that scene, there's a reference where Thomasina is asking Septimus what he's reading, and he says a prize essay from Paris. And in January of 1812, this prize was announced, and it was awarded to Joseph Fourier for his work on the heat equation. That was one of the things that I mentioned that were set up as actual goals to understand things like heat flow purely mathematically. And that paper was absolutely groundbreaking in doing that. He wrote down a mathematical equation, and Thomasina makes this very interesting observation that it differs from Newton in that in the heat equation, time can only go one way, whereas in Newton's laws, you can't distinguish between future and past.
Yes. I gratefully co-opted that.
Where did you get that from? I must tell you, I have never seen exactly that statement anywhere. I've seen other things related to it.
What statement?
That from the heat equation of Fourier, time goes one way, and therefore you can tell the difference between future and past.
Is it true?
It is absolutely true.
You had me worried for a minute. But what I was going to say was that I gratefully, sort of plucked this from somewhere without fully understanding it. I don't really know the meaning of the words that you have just said. I really do not. Are we having a bit of this in the end?
Yes, we are.
We are. Well, I don't want to anticipate either, but I sort of understand it. But of course, I understand it pictorially, and I can see that if you have a movie of a ball just sort of making a parabola. Without other evidence, you don't really know when the movie is going backwards. So I understand what might be meant by Newton's equations. They don't care which way the time is traveling. Right. I can also understand that if the ball smashes a window, then you can tell if the movie is being run backwards, obviously. But where I'm out on a bluff in this scene that you're going to see is that I don't really grasp, because I never did mathematics beyond the age of 17. I don't actually grasp what is meant by the irrecoverable part of the equation being the heat lost in the smash of the glass.
Yeah, well, that really is something a little different. This has to do with entropy and things that were discovered later. That is not part of the heat equation.
This is coming back like a bad dream. I had the most appalling... I was desperate for a connection between entropy and the second law of thermodynamics. And I looked around an awful lot of low-level mathematical literature, and I found it. I'll remember the guy's name in a moment, maybe. He's sort of dubious Belgian Nobel Prize winner.
Him?
Yeah. You know who I mean. Okay. He's absolutely not allowed to... We don't mention him at Berkeley, is this it? Anyway, at the moment, I made this valid association between entropy and heat loss to my complete satisfaction. I have to tell you this. I had no insecurity about whatever.
Right.
Yeah. But I was aware that this was not there on the shelf for the taking. I see that. So I really interrupted you in saying all that because you triggered this memory that I had this problem.
No. It's for me, it was fascinating reading background and discovering things that I didn't know. I knew the entropy part. I did not know the heat equation.
For those of us who are doing theater, could you explain entropy and...
No.
Okay. Well,
I tell you, I was going to explain the heat equation.
I'll do it.
It was told not to. You do entropy.
Okay, I'll have to do it. Okay. Look, you know, entropy is something every mother with a teenage daughter understands, which is that if you just move the stuff around in your bedroom without any plan or thought, it gets untidier. It never gets tidier. So that's what entropy is.
I'm glad I let you do it. Well, before we go on to the last scene, there's just one more thing I wanted to say, perhaps two. As you point out, these are very selected scenes in a couple of ways, just the science and all. But, you know, as I've talked about all the intellectual content and the science you put in, but the thing that I found remarkable about Arcadia is the emotional impact it has. And you get involved with these people in a moving way. And as I mentioned, this last scene refers to Fourier, who had a fascinating life too, but there's no time to talk about it. I did, however, want to mention he did most of his work, for example, his prize paper, when he was a full-time administrator of a prefect of Isère and around Grenoble, and somehow managed to produce this amazing mathematics. He was also very much in with Napoleon, but then with the Restoration, unlike Laplace, he did not keep his position, which was wonderful. He came back to Paris and could do mathematics, finally. And at that time, something I learned recently, he and Sophie Germain became friends. And this quite warm personal relationship developed. They were both, I guess, in their 40s. Neither had married. They were both very successful. Both had a prize essay accepted by the Academy, but were both kind of outsiders for different reasons. So when I read about that, it was a kind of warm feeling, which the personal lives that one doesn't hear much about. And I certainly don't mean to say that Thomasina and Septimus in the heat of their youth are the same, but there's a certain kind of parallel. And I did want to just go on to the last scene now.
I must waltz, Septimus. I will be despised if I do not waltz. It is the boldest and gayest, most fashionable invention, started in Germany.
Let them have the waltz. They cannot have the calculus.
What is your book?
A prize essay of the Scientific Academy in Paris. The author deserves your indulgence, my lady, for you are his prophet.
I? What does he write about? The waltz?
Yes. He demonstrates the equation of the propagation of heat in a solid body. But in doing so, he has discovered heresy, a natural contradiction of Sir Isaac Newton.
He contradicts determinism?
No. Well, perhaps. He shows that the atoms do not go according to Newton.
Let me see. Oh, in French.
Yes, Paris is the capital of France.
Show me where to read. Well, it's just as I said. Newton's machine, which would knock our atoms from cradle to grave by the laws of motion, is incomplete. Determinism leaves the road in every corner, as I knew all along, and the cause is very likely hidden in this gentleman's observation of the action of bodies in heat.
Where does he say?
Nowhere. I noticed it along the way. I cannot remember now.
Nor is he interested by determinism.
Oh, yes. Newton's equations go forward and backward. They do not care which way, but the heat equation cares very much. It goes only one way.
It's heat.
things change, so we are all doomed.
Yes.
It's like a steam engine. You see, she didn't have the maths, not remotely. She saw what things looked like, way ahead, like seeing a picture.
This is not science, this is storytelling.
Oh, is it a waltz now?
No.
Like a film.
What did she see?
That you can't run the film backwards. Heat was the first thing which didn't work that way, not like Newton. A film of a pendulum or a ball falling through the air backwards looks the same.
The ball would be going the wrong way.
You'd have to know that. But heat, friction, a ball breaking a window,
Yes.
it won't work backwards.
Who thought it did?
But she saw why. You can put back the bits of glass, you can't collect up the heat from the smash. It's gone.
So the improved Newtonian universe must cease and grow cold. Dear me.
The heat goes into the mix.
We must hurry if we're going to dance.
And everything is mixing the same way, all the time, irreversibly,
Oh, we have time, I think.
till there's no time left. That's what time means.
When we have found all the mysteries and lost all the meaning, we will be alone on an empty shore.